My name is Stan Carpenter. I'm on the kernel team at Linaro, and one thing that I work on is static analysis with my tool Smatch, which is a static analysis tool that I wrote. It's an open source tool. You can get it on GitHub. What makes it unique, maybe, in open source is that it's got very good flow analysis and it's got cross-function analysis. It's mostly used on the Linux kernel, but you could use it on any C code if you wanted to, probably. I normally give like quite basic talks, but this is a very difficult talk. One of the more difficult programs checks that I've written. We're running out of easy checks to write in static analysis. So they get more and more difficult, so it's good to look at a difficult check to write. So, but here's the introduction to Smatch, what flow analysis means. So it's a state engine, so there's a module which is tracking variables. So that it says that variable A is equal to 1, and then you write the if statement, and you say, oh, okay, variable A is equal to 2. And then if you include the check debug.h file, you can say Smatch implied, and when you compile it, it will say, oh, it's either 1 or 2. Then you write another if statement with a return, and you print it out again, and it's going to say that it is equal to 2. So when you're tracking variables, the flow analysis is a kind of magic that happens in the background to track what state it is at any time. Smatch also has function analysis, cross-function analysis. So it's quite useful for analyzing code, even if you're not looking at static checker output. I use it a lot if I'm trying to understand a new subsystem. So this function, SMDB functions, and then the name of the function. This is a struct member, and it tells you which functions implement that struct member. Then you can look at those and see what they do, how they're implemented. You can copy and paste. This will tell you where a variable is set, and that's very good information, just in general. But mostly, we're using the cross-function database for checking how functions are called and what they return. So this is, you give it a function name, and it'll tell you that it's got 3 callers, and they're all holding a lock. On the first 2, it can't track which parameter is locked, but on the next one, it says that the first parameter 0, is locked. And then it's the same for the return states. That's the same function, and it returns in 5 different return statements. It might not actually be 5 different return statements. We split up the return statements in a kind of meaningful way. So success is important to separate from failure. And so there's 2 successful returns and there's 3 failure returns. So, but they all unlock. That's it, that was the introduction. So the basic locking check works like this. You've got, in the kernel, you've got a spin lock. Then in Smatch, you say, set the state of eLock to locked, or lock, which is quite simple. And then it's the same for the unlock. If you got a spin unlock, you're going to set the state to unlocked. The flow analysis engine is going to track it automatically to say, is it locked now or is it unlocked now? And then they could also be merged. They could be both locked and unlocked. Then you match the lock, you match the unlock. At the end of the function, then you go through all the returns and you say, okay, this return, is it a failure path? And was the was the lock locked? And then also, did we unlock it on the success path? And if so, print error. Because that's the most common locking bug that we see is you have so many return statements, you forget to unlock on one of them. So 5 years ago, I added cross-function support. So this, there's a table that has the name of the locks, so just spin lock, and it says parameter 0, and the $sign here means whatever you pass to parameter 0. And the spin try lock only locks it if you return 1. So you have this table, and it's got hundreds of functions in it. So this is a very confusing function, and I'm not sure I understand it right now, but the way that people use it is they say that if it's 0, we're going to treat it as success. Some of them don't care, but the try lock is straightforward. It returns 1 on success. The other ones return 0 on success. And then the unlock it always succeeds. So you have this giant table that maps directly to the database. And then it kind of seeds the database. So then as we have the database, we have the table, then we fill in the database to say that, okay, on this path, we're holding the lock. In this path, we've unlocked. Like we saw that earlier in the caller table and the return states table. Every time you rebuild the database, it builds on what's already in the database. So, you call it with a function locked, then that one calls it with a function locked, that one calls it with function locked, and I normally say about 5 times if you rebuild it, it basically covers the whole call trees. But you can use Smatch without the cross-function database. The zero-day bot, that's what it does. The cross-function database takes maybe 5 hours or 6 hours to build. So it takes a while, but I rebuild it every night, and I never start again fresh, hopefully. And so my call tree is quite full, I would say. So that's how the call tree works. And the problem was, it's harder than you might think to know what the start state is. If you call spin lock, then you would assume that it was called without the lock held. But sometimes there's functions which are, you pass a parameter and then it's like, oh, we're holding the lock, we're not holding the lock. It's a little bit trickier than you might assume. And then it's especially tricky because sometimes people will lock it with one variable and then unlock it with a different thing, but it's actually the same variable. And so, I was like, well, we could just look at the last bits, right? We could say, oh, if it ends in foo bar, let's assume it's the same. But then you're like, oh, you get some that match by chance and some that don't match, and it doesn't really work very well. So that was quite a big headache. So the other problem is it was quite a big mess because I wanted to change stuff, and I was like, oh, how do I? You get intimidated, and I'm the one who wrote it, but I don't remember what this code does, and then any small change, it's a mess. And then locking information is really, really useful because you might want to write a check to say, oh, when I check, when I access this pointer, is the lock held? But this code was not extensible at all. So it was just increasingly frustrated. So since last Connect, I've rewritten everything. And it's now a modular system. And this kind of provides like a blueprint for how to write modular Smatch checks and cross-function Smatch checks. And as we go forward, more and more interesting stuff happens across functions because we've really run out of like easy checks to warn about. So cross-function is where the interesting stuff is happening right now. So I wrote a module to handle transitions, one module to record when it's holding the lock and it calls a function, one module to say when it drops the lock on the return path. Then there's a separate check to say that, oh, you forgot to unlock on one error path. There's a separate check to say you've taken the lock twice, and there's a separate check to say you've dropped the lock twice. So the transitions, all of this is quite easy. Once you break it up, it all becomes quite easy. With the transitions, you add a hook to say, if people want the locking information, then they can add their own locking hook. And then it uses the table with all the DMA, receive, unlock, and all that stuff. And it also uses the data from the database to say that, oh, we've returned a lock or we've returned an unlock. The caller info records if the lock is held when you call a function. Currently, that's not actually used, but you could use it just to look up stuff, which I do, but it doesn't print out any warnings. But then the return states, which was an enormous source of frustration, becomes very simple. You take the lock, and then if you do an unlock, mark it as ignore. And then you might take the lock again, doesn't matter, it's just ignored. Anything complicated, you just ignore it. Unlock is the same thing, you ignore it. Turns out you do have to record the start state. So if you started unlocked, you take exactly one lock, then that's an unlock or a lock. Now, before I had that thing where I'd look at the last letters in a lock to see if it was the same name with same variable with two different names. Now I've created a new module. So before I mentioned 6 modules, but there's another 7th module, which records the type. So you hook it in, if it records the type to say that it's either locked or unlocked. And then the rule is, if you get to the end of the function and you have 2 locks, and one's a lock and one's an unlock, but you query the type and the type says everything's restored back to the original state, then you say delete that, forget about that. This is not an unlock or a lock function. And that rule is very, very strict because I wanted it to be super strict because I had that problem where I could never get the balance right with the exact number of letters counted or not. But this rule actually works perfectly. So far, wonderful, which is amazing. Guard locks are a new thing in the cleanup.h, and they kind of eliminate all the forgot to unlock bugs. They're a kind of headache from a static analysis perspective because the lock is kind of hard to access. And this is like a conditional unlock. So if the mutex you get, if it's interrupted, somebody press Control-C or whatever, then it returns. And they were all written like that, so they all looked like they could fail. And so I had to go in and edit this file, the db return fixes, to say that actually this function can't fail. It always returns a valid pointer. So that's a function name, what Smatch says it returns, and then what it actually returns. Recently, somebody edited the guard locks so that it becomes, we don't have to do that anymore generally. And the if statements look like if statements, and then the locks that can't fail don't look like they can fail. So for now, I just, they're just parsed automatically, which is great. Some of them I've not entered in the unlocks, but there's no bugs related to that, really. So the improvements are, it's now extensible, so much cleaner. There's so many fewer states to deal with. It's easier to debug. The problem of two names, that's handled correctly. What I realized is that the original code, I'm trying to warn about forgetting to unlock, and I'm trying to remove false positives. So I bias the code to mark things as unlocked when they weren't. But now, with the transition tracking, that's not biased. It's just accurate as can be. And the return states is as accurate as can be. But in the checks, then you can bias it like crazy. And you can bias it in opposite ways, which is great. The checks become much more smaller. And the thing is, you can target the exact check that you're looking for. So forgot to unlock on error path, that's the most common type of bug that we see. And it looks like this. So it works exactly as I described before, but you go through the end and you say, if it's an error code, warn about that. Perfect. Double lock bugs. They're not the same as double unlock bugs. They look completely different. What happens is the person writes a spin lock and they try to write a spin unlock, but they forget and they copy and paste. And so you can first bias it towards marking things as unlocked. And you can say, no, we have to call the exact same function twice because you're looking for cut and paste bugs. Whereas double unlock bugs, how they look like is you take the lock and you unlock before a go-to out, and then the go-to out does a double unlock. So on that one, you look at it and you say, oh, it's both locked and unlocked. If it's not both locked and unlocked, there's almost no point in warning about that. So we're not just looking at what the static checker thinks. We're actually targeting the exact bug that people are writing. And you miss maybe some bugs that way, but you cut down on false positives so much. And because these checks are so small, then you could write another check to look for a different kind of like exact bug that that you've missed, perhaps. So for cross-function analysis, this pattern, I use it over and over again. Transitions, return states, caller states, and then checks. So this works for like reference counting, because functions, they might drop the reference count, and they might increment the reference count. User data, functions get user data, they return it to the other one, and they also pass user data, and that's also very tricky before. I would get it mixed up between you'd pass user data and then you'd return it, or like places that disable IRQs. Any kind of cross-function analysis this is the way to modularize it, I would say. So I don't have a check for double locks across function boundaries. That would be a good one to write. Clang is adding annotation to look at the relationships between locks and the data that it protects, or lock ordering bugs. That would be another good one. And there's ways to infer what lock is protecting what data, because you could look at the lock and then the next line, or the line right before an unlock. So there's ways you could infer that, and that's some work that you could do in the future using the modular system. And because it's so modular, it lets itself be reused, which is nice. So that's it. Thank you very much. Any questions? Yes?
You said that you're focusing on the bugs that people actually write.
Yep.
How are you finding those classes of bugs?
Now, I review git log and commits to stable every couple weeks, every other week, to see if there's anything that could be found with static analysis. I really encourage that exercise, that people should all be evaluating stable bugs just to see how it could be prevented or caught with static analysis or testing. Yep.
Thank you very much. Just curious, how does it compare for other well-known static analyzers such as CPP-check, for example? Just curious if you've been checking. Does it
say the name of the
functions?
static analysis tool?
Yeah, like CPP-check, for example.
Oh, CPP-check.
Like other things that CPP-check doesn't cover, for example. I'm not completely sure, but I think it has thread. Multi-threading analysis too.
No, I'm going to say it does not have
Okay.
cross-function analysis.
Right. Okay. So there are features that are not covered in that.
So in open source, okay. No, in open source, there's not very good flow analysis, and there's no cross-function analysis. So it would be more like a covariety level, let's say. I would say it's up there with the best, let's say. Right. The problem is, outside of the kernel, it hasn't been tested. So outside the kernel, you're out of luck, perhaps, or it might work fine. But inside of the kernel, that's where it's been tested, and like nobody else has customized their code for the kernel like Smatch is. So yeah, by far the best, but also very slow. So that's a disadvantage.
Understood. Thank you very much.
So okay, I'm going to say that Coccinelle is very fast, and also it writes fixes for you, and also it works well with macros. And so Coccinelle has like a lot of advantages. Sparse is very good at like finding endian bugs or user pointers using the kernel space. And for those, Sparse is very fast, and I wouldn't rewrite those in Smatch, because just use Sparse for that. So there's advantages for Sparse and Coccinelle. But in terms of flow analysis and cross-function analysis and finding complicated bugs, Smatch is like the only tool that we have in open source. All right, thank you very much.